Hey everyone. The goal is to do this in one take and as efficiently as possible. But a little bit of theory first. If you already know how to do gas laws and stuff, feel free to skip this. But for many of you who did this lab, you had not been exposed to gases yet. So we'll first start with this ideal gas equation. All right, there's four variables here: pressure, volume, moles, and temperature. R is not a variable, it's a constant. It's called the ideal gas constant. 0.08206, or some people just write a 1, round it up. And then the units are liters times atmospheres over moles times kelvins. Yeah, there's 4 units. And in order to use this equation, you have to have the right units so stuff cancels. So hopefully you can see that you're going one by one. Your volumes have to be in liters. Your pressures have to be in atmospheres. Your moles, well, they'll be in moles. That's the letter N. And then your temperatures must be in kelvins. All right, some common conversions you'll need. 1 atmosphere is exactly equal to 760 millimeters of mercury. And a millimeter of mercury is also known as a torr. All right, that's pressure. Let's see, volume. Volumes are often given in milliliters, right? So just remember to convert that to liters. Moles is easy, all right, and then temperatures must be in Kelvin. So if you need a temperature in Kelvin, you're going to take your Celsius temperature and add 273.15 to it. Okay, so that's the ideal gas equation. Ideal gas meaning a gas in typical conditions behaves ideally. That is to say, your individual gas particles don't really attract to each other too much. And the gases are so far apart, the individual atoms or molecules, you can basically assume their volumes to be 0. So based off of those two assumptions, you get this ideal gas equation. All right, why we care about this so much, why it's so powerful is if you know 3 of the variables, you can automatically solve for the 4th. The one of particular interest to us for this lab was moles. So rearranging the variables and stuff, we get N equal to PV over RT. I like to put my denominators in parentheses. All right, and yeah, just plug and chug. I mean, the way we're used to getting moles is like we measure something in mass, we weigh it, and then we use the molar mass to convert it to moles. Or if you have a solution volume, and you know the molarity, you can get the moles that way. But with gases, if you know the 3 environmental variables of pressure, volume, and temperature of that gas, you can calculate the moles of gas that way. And at Chem 101, we assume that any gas, whether it's like hydrogen gas or helium or carbon dioxide or xenon hexafluoride, whatever, they're all going to act the same. All right, that's pretty cool. So that's the ideal gas equation. And there's one more equation before the next page. This is going to be the, what do you call it? Dalton's law of partial pressures. All right, same Dalton that came up with Daltonism, atomism. All right. Anywho, so what Dalton said is your total gas pressure is equal to the sum of all your individual gas pressures. All right. So like the air in this room right now, we got nitrogen, oxygen, trace amounts of CO2, water vapor. Well, not like trace. The trace stuff is like the argon gas and if you're in Iowa, maybe some radon gas. Anywho, but all the individual gases, they're bouncing around. If you got a pressure sensor, pressure is measured as force over area. All right. So like a nail, you're able to apply a lot of pressure because you have a strong force over a tiny bit of area. It's force divided by area. But in your pressure sensor, the stronger the collisions with your gas on the pressure sensor, the higher the pressure reading. All right, and then each of the individual gases will contribute their own individual pressures. So to get the total pressures, you add up the individual pressures. Or if you know the total pressure, you can solve for any of the missing pressures if you have the other ones. So like in lab today, you measured the total pressure of the lab, and that was, around, I don't know, 670, millimeters of mercury or something, and then to solve for the pressure of your hydrogen gas, you had to take into account that you had water vapor in your sample, and your water vapor, your pH 2O, I think for most people is around like 19 or 20 millimeters of mercury. So to solve for just a hydrogen, you just subtracted 20 out of 670, and bam, like with just math, you got the pressure measurement or calculation, which is pretty cool. All right. So those are the two main gas laws. However, the gas laws chapter is notorious for having billions of little equations, and people feel like they're getting nickeled and dimed like crazy with all these little equations. But here they are, right? This has to deal with a change in the gas. All right? What if you apply a change or multiple changes to a gas? So we're going to start out with PV equals nRT. And we're going to say this is going to be gas before change. Before you do a change. And we'll put ones on everything. R doesn't get a 1 because, well, it's a constant. It doesn't change. And then for the gas after the change, P2 V2 equals N2 RT2. And that's going to be a gas after. Cool? All right. So we're going to set these equal to each other. All right. And we're going to set them equal to R because that's the only constant between them. So doing our algebra, we get, let's see, P1 V1 over N1 T1 is equal to R. And then we can do the same thing for the other side. All right, we get that. So this, I don't know if there's like an official title for this, not that I know of. So I'll call this like the super combined gas law. Okay. And I'll also put here, start here. And we get this result. So the idea goes, if you know 7 of the variables, you can solve for the missing 8th one. That may feel a little bit silly at the moment because, well, you only need 3, and you can solve for the 4th because you can just set it equal to R. But let's just take it at face value for now. Okay. Now from here, we're going to do a bunch of assumptions. All right. I think this is kind of fun. We'll see if you agree. But the first assumption we're going to do is, what if our moles of gas stayed the same before and after we applied a change? We didn't create any new gas particles. We didn't take any away. We didn't condense any of them into like a liquid or solid state or something. All right, everything stayed the same. So if we have that being true, N1 equal to N2, we'll get P1 V1 over T1 equals P2 V2 over T2. And we get this equation. And there's a name for it. I'll do the names later. All right, we can keep this going with a variety of scenarios. The first one we'll do is, what if, in addition to constant moles, we also did constant temperature? All right, if it's the same number, you can just remove it from your algebra. So you get P1 V1 equals P2 V2. All right, and let's just keep this rolling. Let's see what variable we haven't done yet. Let's do pressure next. So what if we had P1 equal to P2 as well? Then we would have V1 over T1 equals V2 over T2. Okay. And we can rewrite this information. I know I'm being redundant, but I don't know if you find that helpful. All right, and then let's keep this going. Let's see, we haven't done. All right, we did the pressure, temperature. I guess that means volume, right? All right, so whoops. V1 equals V2, and of course we're still keeping the moles constant here. Pressure and temperature. Okay, so P1 over T1, P2 over T2. Okay. Good, good, good. We got that. We got. Yeah. All right. So far, so good. And then we can do one more. We're going to go off of this. And then we're going to hold the pressure constant. P1 equals P2 and A and D. We're going to do temperature constant. And then we get V1 over N1 equals V2 over N2. And you know, there's other variations here that I didn't do, but you know, this is limited to your creativity, basically. But these ones, not this one, but this one, this one, this one, this one, this one, these all have names for them. So those are the ones I'm going to go over here. Okay. Me personally, I don't really care if you know the names or not. All right. I feel like people get so worried about like memorizing the names. Oops, I'm off the screen. I'll just drag me. People get so worried about memorizing the names, they often forget that, yo, it's just math. You know, just don't sweat it. Just start from here and then make all your other doohickeys whatever you need. I mean, heck, to be truthful, you could just use this equation, start out with it. And chances are, if they didn't give you all the information, if there's some missing variable information, if you read the problem carefully enough, it's probably just a constant anyways, and you can just remove it and then end up with one of these, all right? So don't overthink this, guys. Now I'm scared that me saying that will make you overthink it. Anywho, all right, here's the names. This is called the combined gas law, this top right one. All right, and then this bottom one is called Boyle's law. All right, I got a corny rhyme for Boyle's law, and it goes, Boyle's not loyal. Boyle is not loyal. All right. The reason why I say that is if you check out the math, it looks different compared to the other mini gas laws, right? So you got 4 mini gas laws. In this one, you have an inverse proportion, an inverse relationship, whereas the other ones are direct. All right, I'll explain that in a minute. Let me just finish with the names. All right, so that's Boyle's law. This one is Charles's law. All right, and then this one is the Gay-Lussac law. Okay. That's not 2 people. That's like a double-barreled last name. Some people or textbooks say Amonton's law. It's the same math. And then this one is Avogadro's law. All right. Same Avogadro that Avogadro's number is named after. And yeah, a lot of his early work was based off of the proportions of volumes with the amount of gases. So since he had worked on moles, moles was named in his honor. So, or Avogadro's number was. So, hey, that's pretty cool chemical history. All right, but those are the names. All right, and in terms of the relationships, I mean, look, if your volume gets bigger, that means you had more gas to maintain that proportion. So in other words, if your volume goes up, that's because your amount of moles went up. So that's called a direct relationship. All right, and Avogadro's law, my favorite nickname for it is the duh law, because hey, if you get more stuff, all other variables staying the same, your balloon's gonna get bigger. You know, you fill a balloon, you put more gas in it, your balloon gets bigger. So Avogadro's law is the balloon law. All right, looks like I'm working reverse here. All right, the Gay-Lussac law. This is pressure versus temperature. So, you know, you heat something up. If its volume is constant, you know, that means you have like rigid walls, right? And the volume can't change. All right, and your gas molecules are stuck, you know, so that can't change either. But whereas like Avogadro's law is often demonstrated in like a balloon or like a piston, you know, stuff that can have its walls move. The Gay-Lussac law, you're gonna have rigid walls. All right, this is like a gas cylinder or something, you know, something closed. All right, or maybe like a can of soda, although like those have some flexibility. But give enough heat, the pressure is going to get really, really high in there until, you know, explodes, right? Or you can do an implosion, right? You can drop the temperature, and then the pressure in there goes down, all right? Okay. And yeah, if the walls break, if your volume gets compromised, then that would shrink too. But this is assuming you're able to maintain rigid walls within the mathematics here. All right, Charles's law, you heat something up, all variables, other variables equal, you heat something up, you're going to make something expand, and the reverse is true. So, yeah, so we have a direct relationship again. Volume up, temperature up. I mean, I could use down arrows here too. But Boyle's law, this is the only one where you have something like some opposite stuff going on. All right? But hopefully it's intuitive. Like pressure means how much like, you know, force you're applying over some area, right? So if you apply more pressure, the volume is going to go down. You're going to crush something. All right? So more pressure, volume goes down. All right. Yeah, you go. The opposite's true, right? You can do like less pressure and like more volume. You take your bag of chips hiking. You know, it's a sealed container. It's got some, you know, gas molecules in there, nitrogen or whatever. You go up, and then it's less pressure in the air. The air is thinner, so with less pressure to press on it, your bag of chips. And same true for like water bottles and whatever. So, yeah, I'm trying to make the case here that all this mathematics is actually rooted in intuition as well. So I think that's pretty neat. All right, so that I meant for that to be like 5 seconds. That was 18 minutes, darn it. But it was kind of important. So that was like the first half of the video. Most of this video is going to be me going over this packet doohickey thing. All right, here goes nothing. Blah 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 blah. All right, so first one was so they're doing Avogadro's law, and basically like we had like vinegar in excess, right? And we just needed the sodium bicarbonate to produce the carbon dioxide. So, you know, you wrote something, you know, in your book, you had like, you know, around that much. You know, and maybe a handful of you spent all the time in the world on the balance just trying to get it to land on there. Anywho, you saw like more bicarbonate, bigger balloons, right? So... all right, we'll get to this in a bit. We'll start with the Boyle's law, not Boyle's law, Avogadro's law, doohickey stuff. All right, so and I know it's redundant to write units when they already wrote it, but that makes me happy. All right, let's do this thing. So, let's see. They want the moles, right? So the equation went, here's acetic acid. There's a little shortcut for acetic acid that the organic chemists use. OAC is what they mean to say CH3COO. And then this is like your acetate part, AC, or acetyl part, and then acetyl turned into an acid. You have that right there. So C2H3O2, and then there's the H plus in the front. So this part is like AC, and then this is like OAC. So like in our class, we write HC2H3O2. But like organic chemists, they just write acetate as OAC. So if you want to save time, I'm just going to do that for this video. And then what do we use? Sodium bicarbonate, NaHCO3. All right, so H plus, HCO3 minus, so we make carbonic acid, H2CO3. Let me just rip this paper. Hopefully I don't lose the order. All right, so we'll get H2CO3, right? But that breaks down into a H2O and a CO2. And then we get our other product, Na with the acetate. All right, or this could be C2H3O2. Whatever. I mean, look, the only parts they really care about in this reaction is this one and that one, and everything's got like easy 1 to 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 1 stoichiometry. All right, but you gotta know where the numbers come from when we do the calculations. So I'm gonna put this one like in a red box, and I'll put the carbon dioxide in like a blue fluffy cloud, all right, for those coefficients. All right, let's convert into moles. Oh, darn it, we need a molar mass. NaHCO3, we got 22.99 for sodium, 1.01 for hydrogen, carbon's 12.01. 3, oxygen, 16 times 3 is going to be 48.00. All right, so we got 1, 4, and then that's how much carried over? Man, I got lost. Okay. No, 1 carried over. Yeah, so 1, 3, 4, 8, 84.01. All right, I know that's right. So here's how you do your calculation. So you got your 100 grams of bicarb, NaHCO3. And I'm writing with a big pen, so I'm going to spill over. So set up my units first. We're going to get 84.01 grams of NaHCO3 for 1 mole NaHCO3. And the answer, all right, 0.1, come on, divide by 84.01. Hopefully I'm on the screen. Yep. 1 point, I'm in scientific. I don't want to. Let's do flow, whatever that means. 0.00119. Yeah. 00119 moles of sodium bicarbonate, and that would be my answer in like this box that obviously I took like way too much room. to do. And then just do the same thing for that. And, this was around double of that. So your answer should be around double. And that is around double of that. So same deal, right? All right. Moles of CO2. Now we get this 1-to-1 mole relationship. All right. Now, I wouldn't play a game of Risk with your instructor. I suspect some would be okay with you just writing the same thing and changing the units. But it does say, like, show your work. So to be technical, this is, the way you would have to show your work. And if you're annoyed because you're like, duh, it's going to be the same answer, I'm glad that you're annoyed. That means you know what's going on. All right, so that doohickey, and then, so we're going to use that one. 1 mole NaHCO3, and then that 1 mole of CO2. So you get the same answer, except you just, change the units, right? But we want to see that process. I know I want to see it, speaking for myself. Because, what if you didn't have 1-to-1 stoichiometry? It's good to just train your brain and not take anything for granted. Okay. Anyways, yeah, you get the same answer numerically. 0.00119 moles of CO2. And that would go in that box. All right, that covers Avogadro's law calculations. So let's see. They gave like instructions in your packet, right? So they're like, questions 1 and 2 involve the same process 3 different times. 3 different times for like your 3 different sodium bicarbonate balloons. So you did that for your 0.1, your 0.2, and your 0.4. And now 3 through 9, they say fourfold because you had 4 different experiments for 3 through 9. You had the 2 known metals, the magnesium, and then you had the 2 known or unknown metals. All right. And in terms of what those unknown metals could be, all right, just as a refresher, we limited our choices to metals that could turn into 2+ cations, give away 2 electrons, because the 2 electrons went into the formation of gas. Okay, so we had some metal, you had 2 HCl, which has pluses and minus, and we had 2 of them. And so the 2 electrons transferred to each of the H pluses there. And then so you got an MCl2 plus a neutral hydrogen with another neutral hydrogen. Well, they form a bond, so you get an H2 gas. All right. Yeah, so to keep the math consistent between the known magnesium and the unknown metal, in terms of this 1-to-1 ratio, we limited it to just +2 metals. So your unknowns, let's have you consider a variety of options. Like this is a whole +2 column, right? But strontium, a little more expensive. Barium's toxic. We ain't gonna choose that. Beryllium's also toxic. We ain't gonna choose that. So I guess your unknown could be magnesium again, but it could have been calcium. Let's see. All the metals. Oh, this is a really wide menu. All the metals here are capable of forming 2 pluses, but vanadium in high quantities can be a little bit toxic, and it's going to be a more expensive metal. So I'll just let you know it ain't going to be that. Let's see. Iron, there's iron. Iron's more accessible often in the 3+ oxidation state compared to the 2. You can play that game with iron. In nature, iron 2+, iron 3+, and like minerals out there, it's about 50% for each oxidation state. Actually, a little bit more in the 2+, now that I think of it. Well, I guess maybe iron's a possibility then, huh? But I'm going to take the words of one of your classmates. One of your classmates said this. Hey, don't all these metals, if they're dissolved in water, form ions that have color? You know, like copper and water, it can be like blue or green, and et cetera, et cetera. Yeah, good point. So colored in a solution, aqueous solution. Okay, you know, we have blue, green. I mean, iron in right conditions, you can, you know, you got oranges or even purples, you know, you can get all sorts of cool stuff. So manganese can be purple in the right conditions, but I don't know, look up zinc. It doesn't have any color in solution, so maybe that's a possibility. And then, yeah, no 2 pluses here. I mean, I guess lead, but we're not going to. I mean, maybe. I gave away too much. I'm just gonna be quiet now. All right. We gotta do all this stuff. Darn it. All right. So here we go. I'm going to. I need to get some numbers. Hang on. Be right back. All right, here's my first page of data. So 677.6 millimeters of mercury total. That applies for everything. We're going to, the unknown I have is not any of yours. So don't be thinking that my unknown, I mean, I guess it could have been yours. Well, I just gave it away again. If it isn't obvious, I don't gamble. I don't have a poker face. I don't know how to lie. So, so 677.6, 21.1. But we're going to need this in kelvins, right? So, man, I've been talking a lot today. So 21.1 plus 273.15. So we're going to get 294.3 because we can only stop in the 10th place. I mean, I guess you could write a 2.5 and carry over to rounding extra digits to minimize rounding error, but I can tell you pretty confidently for this lab, you're going to be all right. I mean, heck, your metal ribbon masses only have like 2 sig figs on them, so something with like 4, that's good. All right, and then we need to go to the table to get the pressure of the water vapor based off of 21.1 degrees C. 21.1 is nearest to 19.8. Looks like this table doesn't like do a great job of getting to all the temperature possibilities, but it'll be okay for this lab. So 19.8. And we put that right here. All right, next page. All right, so let's keep going. Let's finish up this pressure stuff. So we had 677.6 minus 19.8, 657.8. And then converted to atmospheres, we divide by 760. Okay, if you wanted to do that like dimensional analysis style. It's like that. All right. What was the answer? 0.8655. Okay. Atmospheres. All right. So to keep life simple, we said just use the same pressure, and temperature for all your gases. We didn't require you to do like different readings for each one. But of course, you had different volumes for each of your different gases, okay? And basically it went like this. The more metal you had, the more gas you'll produce, right? But nothing else changes in this experiment. So yeah, so we had 45.9 mils for whatever my unknown metal was, and then I'm going to convert that to liters by dividing it by 1,000. I could have done that in my head, but I don't know. I'm tired and I have a headache like most of you, right? So 0.0459 liters. And then time to get that into moles. So let's see. Let's do a checklist. All right, we had a lot of stuff going on. So we need... So this number's important. This number's important. And then the kelvins is important. The other stuff, meh. Okay, they're in units that we can't work with. So we're solving for moles, right? So I'm getting to my ultrafine Sharpie here. PV equals nRT. And we need the moles. So that's going to be N equals PV over RT. All right, so the pressure I got it from the pH2 ATM box. I'm still going to run out of room even with fine tip. Let me see. Volume. All right, this one. So VH2 in liters. And of course, you're going to have different data than me, but if you can't get like reasonable numbers or you're lost, my advice to you is see if you can get the same numbers as me first. All right, gas constant R is always 0.08206 liters, atmospheres over moles, kelvins. And then our temperature on the previous page was 294.3. Kelvins. Okay. Unit cancellation. Our atmospheres go, our liters go, our kelvins go. And we're left with moles. 1 over moles is moles. Okay. If you forget that, 1 over x equals x. And as a reminder, you could do 1 divided by half for an example. A half fits into a whole 2 times, thus proving that. All right, anywho, let's calculate this. 0.8655 times 0.0459 divide, start parentheses, 0.08206 times 294.3 close parentheses. Hit equals, and we get 0.001, let's see, sig figs 3. That's our lowest number. Yeah, so that has 4, 4, 4, 3, 1, 6, 4. I don't always do this when teaching 101, but I am actually going to carry some extra digits. I could carry like 497 extra, but that basically rounds to a 5. So I'll just carry like 1 extra. like that'd be 50, but it's a 0, so meh. All right, so 0.001645 moles of hydrogen gas. So without weighing our hydrogen and using the molar mass of hydrogen, 2.02, and converting it into moles, we used environmental variables to calculate the moles of hydrogen. I think that is wicked awesome. Not only that, but gases like don't weigh a lot anyway, so that's pretty hard to do. And that would be my answer into that box. For showing your work and all that, probably like use like different scratch paper or whatever. This is like not enough space. All right, now moles of metal. Now we have the 1-to-1 stoichiometry that we promised earlier. I'll just rewrite that equation. We had metal plus 2HCl giving us metal chloride, 2 chlorides, right? And then an H2. And we had that 1-to-1 stoichiometry between the hydrogen and the metal. So I'll go to my old codes again of box. I'll use red box and blue fluffy cloud. All right, so I'll take that number, 0.00164. My 5 is not significant, so I like to write it lower when it's not significant. And I'm just trying to minimize rounding error. If you're like, I don't want to carry anything beyond the bare minimum sig figs. For 101, I am totally okay with that. 0.00164. And then 5 moles of H2. And then we react on a 1 mole H2 per 1 mole metal basis. I'm just going to use M for metal. And that 1 I got from the red box. And then that 1 I got from the blue fluffy cloud. But anyways, it's just the same number. But now we have done the conversion into metal moles. All right, we're pretty close. Molar mass is grams of metal divided by moles of metal, and that gives us grams per mole, molar mass. So I had 0.064 grams of metal, and that's only 2 sig figs. All right, this is not a high precision lab, folks. Like we have balances that give more decimal places, but with the hundreds of people we have in 101, we don't want to risk those when they're thousands of dollars. So sorry. If you ever want to see it, I'm happy to give you a tour. 0.001645. So I'm taking my mass of metal. Oh, there it is. Mass of metal, and then dividing it by my moles of metal. All right, moment of truth. What do I have? I have 38.9, so that's going to round up to 39. Grams per mole. Now, if I had another trial, let's say, my second trial, I got 37 grams per mole. Obviously, you have to do the actual work. Nana and a boo-boo. I don't. But 39 plus 37 divided by 2 of that addition answer, I'd get like 38, right? And then, that'd be my answer. So I look for the nearest reasonable metal to 38. So it's not going to be zinc, it's not close to any of these. Plus I didn't have color in solution anyways. It's not magnesium. But maybe it's calcium, like 37, 38, what did I get again? 38, with a high of 39, like it's calcium's the only reasonable option. I wouldn't conclude potassium because potassium, number one, is dangerous. Number two, it doesn't work with the same stoichiometry of a 1-to-1 relationship. Like proving that if you were to drop potassium into hydrochloric acid. I mean, potassium's so unspecific anyways, it's going to react with just the water itself. But if you were to isolate this somehow, you'd get KCl, and then you get a H2. And we would need a 2 here. Which means we would need a 2 there, and then a 2 there. And so potassium, basically, because it's a 1+, it would give you would need 2 potassium for every 1 hydrogen generated. So you'd get half the amount of gas from a potassium compared to a +2 metal. All right. Anyways, yeah, and then that's the identity. Now, after such, I think for a lot of students, they find out what their metal is. Oh, that's cool. That's great. And you feel like you're done. And then these last 2 equations, after like such a emotional high of figuring out a metal based off of gas release, then you're like, why are we calculating this random stuff now? Well, we're trying to show one more point at the risk of teaching too many things, and it's this idea of ideal molar volume. Okay, I think it's pretty nifty. So let's just do it. So we have to do this so-called STP calculation. So that goes back to the beginning of the video, where we talked about like the different gas laws and whatnot. And so we're going to use the combined gas law. And we're going to rewrite it this way. We're going to rewrite it. Same thing, just different labels. Okay. We're going to have P, am I on the screen? H2VH2 TH2 over PSTP VSTP TSTP. And they want you to solve for this one. So basically, we're trying to answer the question, if we were at ideal conditions, I have to put a quote on that as well. Quote within a quote. I'm sure I'm breaking some English law here. If we were at ideal conditions, comma, what would have been our volume? Okay. Ideal conditions, it's a horrible term because that's like assuming that everyone on Earth is inferior compared to this ideal condition, but whatever. Ideal conditions means 1 atmosphere exactly. And where they got that from, like 1 atmosphere is at one point they measured the height of Mercury at sea level, and it was around in your mercury barometer around 760 millimeters of mercury. And then so once that kind of became consistent, measuring at sea level, it's like, what, let's just call 760 exactly 1 atmosphere. And so that's where that conversion came from. Okay, but since it's 1 atmosphere exactly, you can write 1.2, give yourself all the sig figs you need. Or just write that and know it's infinity sig figs. So that's ideal. What's this? Pressure? Yeah, so that's your ideal pressure. And then your ideal temperature. They wanted a common frame of reference to be freezing conditions. Okay, so that'd be 0 Celsius exactly. But you can't use Celsius in gas laws because negative numbers are possible. And that would lead to negative answers. And so that's why Kelvin was developed, right? And to get Kelvin, you just slap 273.15 into that. So this is your ideal temperature. Okay, so ideal temperature would be T STP. STP again is for standard temperature and pressure. So that's TSTP. And then this is your PSTP. All right, so after all that rigmarole, it just boils down to, hey, just take these two and do plug and chug there for those. All right, and then pH2, VH2, TH2, that's just the same stuff you used earlier on your sheet that we put the check marks by. All right, this one, that one, and then the temperature one. I have such a big pile of papers, I don't know if I'm going to find it. Oh, there it is, that one. All right, let's rearrange the algebra and just solve. Okay, just drag that over. Now these going to the other side will flip. And an extra confirmation of that is we have to be left with a volume. And so we would need pressures to cancel and temperatures to cancel, leaving us with just the units from that volume. All right, boring plug chug, boring plug chug. I'm going to pause this video instead of having you sit through the pain of me grabbing those numbers. Or maybe not. Too tired. 290. All right, so I had 0.8655 atmospheres. I'm going to run out of room, aren't I? Times 0.0459 liters times TSTP 273.15 kelvins. Let me just get rid of this. Go away, go away. All right, that's my numerator. I know I don't need parentheses, but whatever. All right, and then for the denominator, you need parentheses. TH2 294.3 kelvins. And PSTP is, oh, that's easy, 1 atmosphere exactly. Okay, so again, units will cancel except for liters. And then now we can put this thing into the calc. All right, so 0.036, okay, 36 figs, so 369 liters. All right, if you're curious what that'd be in milliliters, just move it over 3 times, right? So you get 36.9 milliliters. So, yeah, that's definitely a different amount of, not different amount, but different volume of gas. Like here in Twin, 45.9 liters. But yeah, I guess if you're at a higher pressure, that will have a measurable effect on the volume, as well as a different temperature will shrink things as well. So 36.9 milliliters. But they wanted the liters, so we'll just put the liter amount. Okay. All right, and then the last part is something called molar volume. All right, VSTP molar. Okay. This is our way of saying, hey, for 1 mole of gas under STP conditions, how much volume would that 1 mole occupy? So this is going to have units not of liters, not of moles, but of liters per mole. Okay, the volume for 1 mole. So to do that, you will take your STP volume and then divide it by your moles of gas, which is this box of NH2, 0.001645. All right. And I'm hoping this is kind of a cool result. But I am aware not everyone will care or agree. Whatever. 22. Well, see that. I still somehow always get a surprise when it lands right on the dot. 22.4 liters per mole. What is so good about 22.4 liters per mole? This is what's so cool about it. This is true for all ideal gases. Okay, all. So 1 mole of any gas at STP, if you're at sea level on a freezing day, okay, exactly the freezing point. But anyways, you have 1 mole of any gas, any gas, hydrogen, helium, whatever, okay? This is approximately the amount of space it will occupy, 22.4. And I use the word approximately because not in the scope of Chem 101, but for the handful of you that will go on to take on more chemistry and or physics courses, you'll eventually learn about how not all gases behave ideally, at least not under all conditions. So there'd be little variance of that. But yeah, as like a back of the envelope sort of rule of thumb, if you have a mole of gas, it's going to occupy around 22 liters, regardless of the gas. I think that is pretty cool to just have that as a rule of thumb. Let's see, was there anything else? I don't think there was. Oh yeah, and then just write that good old conclusion. Blah, blah, yakety smackety. All right, 56 minutes. Holy moly. Well, I'm ready to eat and relax, and hopefully you the same after you go through this video. Have a good night. Take care.